Hi, I'd like to tell you about a quantity called rotational inertia. Sometimes it's called rotational sluggishness, and sometimes it's called the moment of inertia. In any case, all three of these can be designated with an uppercase I, a capital I. All right, so it turns out that to rotate something about an axis, when we rotate it, say, about, let's say, this axis. I'm going to put an axis right through here. Like that. That's the axis. Then as this rotates around, so maybe it would go like this. This one would go down, and this one would come up at us, so like that, and go like that. If you want to know just how sluggish this is about this axis, how sluggish it is to rotate about that axis, then what you do is you use the following equation for I. Here's just the basic equation, the simple equation for I. It doesn't just depend on mass. It depends on how far the mass is from the axis of rotation. In fact, it depends more on how far it is from the axis than on just how much mass it is. Because it'd be M1 times R1, but the R1 gets squared, plus M2 times R2 squared, plus M3. And you do this for however many masses you have, M3 squared, dot, dot, dot. Okay, so let me calculate what the rotational inertia is for this object about this axis. Okay, so I is equal to, that's 1 kilogram, and if this is 2 meters, and that's 1 meter, then that would be 1 kilogram times 1 meter. That's 1 meter from the axis, so 1 kilogram times 1 meter, and we'll square the 1 meter. Plus 2 kilograms times 1 meter, and we'll square that 1 meter. Oops, we'll square it like that. Plus, coming down here, 3 kilograms times how far it is from the axis, so that's 1 meter squared, plus 4 kilograms times 1 meter squared. So let's see, that's going to be 1 kilogram meter squared, 2 kilogram meter squared, so that's 3, 6, 10. So the rotational inertia for this is 10 kilograms meter squared. That's the units for I. Now I want you to notice something. If we choose a different axis, say we choose the following axis for this, instead of that one, we use this axis. Well, intuitively, is that going to give you more rotational inertia or less rotational inertia? And the answer is that it's going to give you less rotational inertia. And the reason for that is because these masses are a little closer to the axis. So it's a little easier to spin that way. It's easier to spin around this axis than it would have been to spin around a different axis. That's kind of like with this pen. If I rotate it this way, that's a certain amount of rotational inertia. This would be a different amount. If I rotate it that way, it's actually less rotationally inert if I rotate it about this axis than about this one. It's the most rotationally inert about this one. Yeah, that's a lot tougher to rotate around that axis, or this way. That's a tough axis to rotate around. This is a little easier. This is the easiest still. Okay, so that all said, let's calculate what it is. So I, now if this is 1 meter across, then that's going to be, I is going to equal 1 kilogram times a half meter squared plus 2 kilograms times a half meter squared plus 3 kilograms times a half meter squared plus 4 kilograms times a half meter squared. They're all a half meter from the axis. Okay, well, when you square a half, you get a quarter. So this is going to be equal 1. This one will equal a half, so that's 1 1/2. This will equal a quarter, so now we have 1.75. So I is 1.75 kilograms meters squared, plus that's going to give me 3/4. So that gives me 2.5 kilograms meters squared. That's what I is. Okay, those aren't the only two axes. We could, there's another axis that we could spin this around. There's actually an infinite amount of axes we could spin this around. But here's another one. We could have the axis going in and out of the page, in which case this thing would spin like this. It would spin, whoop, it'd spin like this. And then you would be using this distance. That's how far it is from the axis. We could use this axis. In which case, if we found the I for this axis, it'd be 1 kilogram times 0, plus 2 kilograms times 1 meter squared, plus 4 kilograms times 1 meter squared, plus 3 kilograms times 0 again. So rotational inertia, or rotational sluggishness, that's a little bit more complicated than just regular inertia. M is the mass is the regular inertia. Okay, I think I'll end this there at 7 minutes and 18 seconds. All right, see you.